A deep dive into network highways, transmission media, wireless, and traffic control. Welcome to an even deeper exploration of the intricate world of network highways. This extended version dives further into the technical aspects of transmission media, wireless communication, and network devices, providing a comprehensive understanding of how information travels through our digital landscape. Transmission media, the underlying infrastructure. Cable media, a closer look. Twisted pair cable. Beyond the basic design, twisted pair cables come in various categories, each with different characteristics. UTP unshielded twisted pair, the most common and cost-effective option, often used in Ethernet networks. However, UTP cables are susceptible to crosstalk, where signals from nearby wires interfere with each other, limiting data transmission speed and range. STP shielded twisted pair includes a metallic foil or braided shield around each twisted pair, providing better protection against crosstalk. This allows for higher data rates and longer cable lengths compared to UTP. Commonly used in industrial environments or areas with high electrical interference. Scandinavian telephone cable SCTP, a specialized type of twisted pair cable with tighter twists and improved insulation, offering superior performance over UTP in terms of data rate and noise rejection. Often used in telephony applications. Coaxial cable. This cable offers significant advantages over twisted pair due to its shielded design. The central conductor transmits the signal, while the braided shield blocks external interference. This allows for higher bandwidth and longer transmission distances. Here's a breakdown of different types of coaxial cables. RG58, a common type used for short-distance applications like connecting cable TV outlets or antenna connections. RG6, the standard cable used for cable TV installations and Internet access via coaxial connections. Offers improved bandwidth compared to RG58. RG11, a thicker and more robust cable used for longer distances and higher bandwidth applications, such as satellite TV connections. Fiber optic cable. This high-performance option uses light pulses to transmit data. Light travels through the core of the fiber optic cable with minimal loss, resulting in significantly faster data rates and longer transmission distances compared to copper cables. Here are common types. Single-mode fiber, uses a single, thin core fiber to transmit light. Offers the highest data rates and longest distances, but requires specialized equipment for connection. Used in long-distance backbone networks. Multi-mode fiber, uses a wider core that can transmit multiple light modes, making it easier to connect compared to single-mode fiber. However, it experiences higher signal dispersion, limiting its data rate and range. Commonly used in shorter distance applications like building backbones and data centers. Wireless media, diving deeper into radio waves. Wireless communication utilizes radio waves of various frequencies to transmit data. The choice of frequency impacts range, data rate, and penetration through obstacles. Here's a breakdown. Radio frequency RF spectrum, the entire range of electromagnetic frequencies used for wireless communication. This spectrum is divided into different bands with varying characteristics. Lower frequencies offer longer range and better penetration through obstacles like walls and buildings, but have lower data rates. Examples include radio waves used for AM/FM radio broadcasting. Higher frequencies provide higher data rates for faster transmission but of shorter range and are more susceptible to blockage by modulation techniques. These techniques convert digital data into a format suitable for transmission over radio waves. Common methods include amplitude modulation. AM varies the amplitude strength of the carrier wave to represent digital data. Used in AM radio broadcasting. Frequency modulation. FM varies the frequency of the carrier wave to represent digital data. Offers better noise immunity compared to AM. Used in FM radio and some cellular networks. Quadrature amplitude modulation. QAM combines amplitude and phase variations of the carrier wave to encode multiple bits of data into a single symbol. Used in high-speed wireless networks like Wi-Fi and cellular technologies. Wireless standards, these define communication protocols and specifications for different wireless technologies. Examples include IEEE 802.11 Wi-Fi, a family of standards for wireless local area networks VLANs, providing internet access and device connectivity within a limited range. Different versions offer varying data rates and ranges. Example, 802.11 acres, 802.11x. Cellular network standards, these define protocols and specifications for mobile phone communication. Common standards include 2G GSM, CDMA, the first generation of digital cellular technology, offering basic voice communication and limited data capabilities. 3G UMTS, CDMA 2000, enabled faster data transmission for internet access and basic multimedia applications. 4G LTE, significantly increased data rates and improved network capacity, supporting mobile broadband and streaming services. 5G, the latest standard offering ultra-fast data speeds, low latency delay, and network slicing for diverse applications like the Internet of Things IoT and autonomous vehicles. Signal degradation and error correction, as data travels through any transmission media, it can degrade due to various factors. Attenuation, signal strength weakens over distance. This is more pronounced in higher frequencies used for wireless communication. Noise, electrical interference from external sources can corrupt the signal. Distortion, the signal shape can be altered during transmission, leading to errors in received data. To combat these issues, error correction techniques are employed. These techniques add redundant information to the data stream and use algorithms at the receiving end to detect and correct errors. Examples include, forward error correction FEC, adds redundant data to the original data stream. The receiver uses this information to identify and correct errors without requiring retransmission. Checksums, a mathematical calculation applied to the data to create a value. The receiver recalculates the checksum and compares it to the transmitted value. Any discrepancies indicate errors in the data. Network devices, the guiding force. Hubs, a simple but limited solution. Hubs operate at layer 1 physical layer of the open systems interconnection OSI model. They receive data on one port and simply broadcast it to all other connected devices. This approach has limitations: collisions. If multiple devices attempt to transmit simultaneously, the signals collide, corrupting data. This becomes more problematic with increased network traffic. Limited security. All devices on the network can see all the traffic, raising security concerns. Inefficiency. Unnecessary broadcasts of data to devices not intended for the message waste network bandwidth. Hubs are a simple and inexpensive solution for small networks with minimal traffic, but are not suitable for larger or more demanding environments. Switches, the intelligent traffic directors. Switches operate at layer 2 data link layer of the OSI model. They maintain a table that maps MAC addresses to their corresponding ports. Here's how they work. Learning. When a device transmits data, the switch learns its MAC address and the port it's connected to. Filtering. The switch receives data and examines the destination MAC address. It then forwards the data only to the port where the intended recipient is connected. Collision reduction. By directing data only to the intended port, switches significantly reduce collisions compared to hubs, improving network performance. Switches offer several advantages: improved efficiency, data is directed only to the intended recipient, reducing unnecessary traffic. Reduced collisions, significantly lowers the chances of data collisions, leading to faster and more reliable communication. Increased security. Devices can only see traffic intended for them on the specific port they are connected to. Routers, the navigators of the network. Routers operate at layer 3 network layer of the OSI model. They connect different networks and act as intelligent gateways, directing data packets to their final destination. Here's how they work. Routing protocols. Routers use routing protocols to communicate with other routers and learn about the network topology layout. Packet forwarding. Routers analyze the destination IP address of each data packet. Based on the routing table and network information, they determine the best route for the packet to reach its destination. Internetwork communication. Routers enable communication between devices on different networks, such as connecting your home network to the broader internet. Routers provide crucial functionalities: internetwork connectivity. They allow devices on different networks to communicate with each other. Packet forwarding. Routers intelligently route data packets to their intended destinations across complex network structures. Security features. Routers can implement security features like firewalls to control access and filter incoming advanced network devices. As network complexity grows, additional devices play crucial roles. Bridges. These connect two or more LAN segments, filtering and forwarding traffic based on MAC addresses. They can alleviate congestion by segmenting large networks but are less intelligent than switches when it comes to traffic management. Repeaters. These regenerate weak or degraded signals to extend the reach of transmission media. However, they amplify not only the signal but also any noise present, potentially causing issues. Repeaters operate at layer 1 physical layer and do not distinguish between different data packets. Firewalls. These act as security barriers, filtering incoming and outgoing traffic based on predefined rules. Firewalls help to protect networks from unauthorized access, malware, and other security threats. They can be implemented in hardware, software, or a combination of both. Load balancers. These distribute network traffic across multiple servers or network links to improve performance and prevent overloading any single resource. This is particularly important in high-traffic environments like web servers or cloud computing environments. Network Access Control (NAC). These systems enforce security policies by identifying and authenticating devices attempting to connect to a network. NAC solutions can restrict unauthorized access and ensure only authorized devices with proper security configurations can participate in the network. The future of network highways. The landscape of network technologies is constantly evolving. Here are some emerging trends shaping the future of network highways. Software-defined networking (SDN). This approach separates the control plane network management from the data plane data forwarding. This allows for more flexible and programmable network management, enabling quicker adaptation to changing network demands. Network Function Virtualization (NFV). This virtualizes network functions traditionally performed by dedicated hardware appliances. This allows for greater agility and scalability by running network functions on standard servers, improving cost efficiency and simplifying network management. Li-Fi Light Fidelity. This technology uses light waves for data transmission, potentially offering higher bandwidth and faster speeds compared to traditional Wi-Fi. However, Li-Fi has limitations in range and requires line of sight between the transmitter and receiver. Satellite Internet Access. Advancements in satellite technology are making satellite internet a more viable option for remote areas where traditional cable or fiber optic connections are unavailable. Low Earth orbit (LEO) satellite constellations are being deployed to offer wider coverage and lower latency compared to traditional geostationary satellites. Conclusion. Understanding the intricacies of transmission media, wireless communication, and network devices is fundamental to navigating the complex world of network highways. By employing the right technologies and configurations, we can create robust, efficient, and secure networks that support our ever-growing reliance on data and communication. As technology advances, exciting new possibilities will emerge, further shaping the future of how information travels across the digital landscape. Network Highway Quiz, testing your knowledge. Question: what are the two main categories of transmission media, and what are some real-world examples of each? Solution: cable media. These are physical cables that connect devices directly. Examples include twisted pair cable, used in Ethernet networks for connecting computers within a building. Coaxial cable, used for cable TV connections and Internet access via coaxial connections. Fiber optic cable, used for long-distance data transmission due to its high speed and immunity to interference. Wireless media, these utilize radio waves to transmit data without cables. Examples include cellular telephone networks. Mobile phones communicate with nearby cell towers to connect to the network. Satellite networks. Data travels vast distances via satellites orbiting Earth, ideal for remote locations. Question: what are the key differences between twisted pair and coaxial cables? Solution: twisted pair, more affordable, uses two insulated wires twisted together, susceptible to crosstalk interference and lower data rates. Coaxial cable, more robust with a central conductor shielded by a braided mesh, offers higher data rates and better protection against interference compared to twisted pair. Question: what are the advantages and disadvantages of using fiber optic cables? Solution: advantages: fastest data transmission speeds, immune to electromagnetic interference, long distances supported. Disadvantages: more expensive than copper cables, requires specialized equipment for installation. Question: how do radio frequencies impact wireless communication? Solution: lower frequencies offer longer range and better penetration through obstacles but have lower data rates. Example: AM/FM radio. Higher frequencies provide higher data rates for faster transmission but have shorter range and are more susceptible to blockage by obstacles. Example: microwaves, millimeter waves used in cellular communication. Question: what is modulation, and how does it play a role in wireless communication? Solution: modulation is the process of converting digital data into a format suitable for transmission over radio waves. Different modulation techniques encode data by varying the amplitude, frequency, or phase of the carrier wave. Question: what are the limitations of hubs in network communication, and how do switches address these limitations? Solution: hub limitations, collisions. Data corruption occurs when multiple devices transmit simultaneously. Limited security, all devices see all traffic, raising security concerns. Inefficiency, unnecessary broadcasts waste bandwidth. Switch advantages: learn MAC addresses and direct data only to the intended recipient, reducing collisions and improving efficiency. Offer increased security by limiting what each device sees on the network. Question: what is the primary function of a router in a network? Solution: routers connect different networks and act as intelligent gateways, directing data packets to their final destination across complex network structures. They analyze IP addresses and use routing protocols to determine the best path for efficient data delivery. Question: describe the difference between a bridge and a switch in network communication. Solution: bridges connect two or more LAN segments, filtering and forwarding traffic based on MAC addresses. They can alleviate congestion by segmenting large networks but are less intelligent than switches when it comes to traffic management. Switches learn MAC addresses of connected devices and direct data only to the intended recipient, significantly reducing collisions and improving network performance. Question: what are some security features that routers can offer to protect a network? Solution: firewalls filter incoming and outgoing traffic based on predefined rules, protecting against unauthorized access, malware, and other threats. Network address translation (NAT) hides internal network IP addresses from the Internet, adding a layer of security. Question: briefly explain two emerging trends that are shaping the future of network highways. Solution: software-defined networking (SDN) separates the control plane network management from the data plane data forwarding. This allows for more flexible and programmable network management, enabling quicker adaptation to changing network demands. Network function virtualization (NFV) virtualizes network functions traditionally performed by dedicated hardware appliances, improving cost efficiency and simplifying network management by running these functions on standard servers.